Hello, and welcome to the video portion of the simulation lab for ME123. Today, we're going to have a brief introduction to finite element analysis and stress-strain simulations. When designing components that need to withstand some force or load, it's important to know that the component won't bend too much or break while performing its function. Of course, in this arena, nothing can beat physical testing. However, physical tests are often expensive and time-consuming, so having a virtual method to get preliminary results is a handy tool for any engineer's tool belt. Before we begin, this lab is going to be using SolidWorks Simulation, a premium plugin for SolidWorks. SolidWorks Simulation is installed on the remote desktop version of SolidWorks, but the full version does not come packaged with the standard student license of the product. You will need to be on the remote desktop version of SolidWorks to use most of what we cover today. Now, let's begin with defining some terms. As this is a brief introduction, these definitions are simplified for our purposes, and more information can be found online or in future engineering courses. Force is how much something is being pushed or pulled. It is often measured in newtons or pounds. Stress is how much something is being pushed or pulled, divided by the area that the force is being applied to, often measured in pascals or psi. A higher force and a lower area leads to an increased stress. When a material experiences stress, it often stretches or compresses, changing its length. The amount of length change, divided by the original length, is called the strain. Strain is often measured in millimeters over millimeters or inches over inches. Below certain stresses, many engineering materials have a linear stress-strain relationship, meaning that the strain the material experiences is directly proportional to the stress it experiences. In other words, if you pull on it twice as hard, the length will change by twice as much. The measure of how much the material resists deformation under loads is called the elastic modulus, or the Young's modulus. Different materials have different moduli of elasticity. Finally, after a certain stress threshold is reached, the material starts experiencing plastic deformation, meaning that releasing the stress will no longer allow the material to return to its original state. Think of how you can pull a spring a little bit, but then when you release the force, it will return to its starting shape. This is because you remained below the yield stress and the material only experienced elastic deformation. However, if you pull too hard and then release the stress, the material stays bent as it's experienced plastic deformation. This threshold is known as the yield stress, and it defines the stress at which the material fails, which is the final important piece for our preliminary introduction. In short, parts designed for engineering applications often have to withstand some load, which applies stresses to the material. The material then experiences strain based on the properties of the material. If the material experiences too much stress, it is permanently deformed, which will be considered part failure for our purposes. As mentioned earlier, this is a very brief overview of material that has years of coursework related to it. While this description is overly simplified, it will serve to give you a background for what we're doing today. So, now that we have some background, let's ask a few questions. Will my part fail while it's doing its job? Where will be the most likely places for the part to fail? If the part does not fail, how much more force could it take before it would? These are common questions in engineering, and while finite element analysis won't give us perfect answers, it allows for some quick, cheap testing to be done before performing more accurate, expensive tests. Okay, talking about all of this in the abstract is tough. Let's ground things in an example. Here, I have a metal shelf that I've designed to hold my engineering books. This shelf is made of steel sheet metal, and it attaches to the studs in my wall through these 6 bolt holes on the back. My books would sit up on this surface on top. These things must weigh at least 200 pounds, so I want to know if the shelf I made will be able to support them. Let's boot up SolidWorks Simulation to find out. Once we've finished our model, the first step is to check to make sure that the plugin is active. We can do this by navigating over to the SolidWorks Add-ins tab on the ribbon and making sure that the SolidWorks Simulation button is selected. From here, we can navigate over to the Simulations tab and select the Study button to begin their simulation. Okay, well, that's a lot of stuff we don't have time to cover. For our purposes, and the purposes of anything below a 300 level course, we're just going to leave this at static and hit the green checkbox. Cool, let's see what we've got. Going from the top down on our new study, we can see that we're testing our bookshelf, which is made from plain carbon steel. We can right-click and select Apply Edit Material to change the material, but steel sounds right here. For time and sanity, I'm going to skip over connections and go straight to fixtures. Fixtures are the rules that our part has to follow, and are often used to connect our model to its environment. There are a lot of different types of fixtures, but we'll get into the details later. Next up, we have external loads. These allow us to define the forces and pressures acting on our object. Continuing on, we have mesh. As mentioned earlier, SolidWorks Simulation is a type of finite element analysis software. As one could guess by the name, this software works by breaking the model up into a finite number of elements and analyzing them individually. In less snarky terms, this means that we're going to be splitting up the whole part into a lot of smaller pieces and working through the problem bit by bit. This involves a lot of complex algorithms and matrices, with entire courses worth of material discussing the math behind the calculations involved. However, that goes beyond the scope of this class, so we're just going to hand-wave exactly how it chooses to use the pieces, and just go straight into the results. In short, the mesh options here allow us some control over how SolidWorks cuts up our model. Finally, we have the results options. From here, we can choose what we want to know about the model. We can also find out what sections are experiencing the highest stresses, what sections are getting moved the furthest from where they started, and which sections are the closest to breaking. But before we can do any of that, we need to set up our fixtures. We can do this by right-clicking our Fixtures option and selecting Fixtures Advisor. From here, we can select Add a Fixture and see what our options are. For the purposes of today's video, we're mostly going to be sticking to the standard fixtures. Fortunately, SolidWorks gives nice descriptive animations for each one of our options. Fixed geometry locks a surface, point, or edge into its current position. This works well for things that are glued, riveted, or bolted. With the fixed option selected, let's choose the 6 inside surfaces of the cylindrical cuts on the backside of our object. Cool! This gives us the 6 fixed features. We can hit our checkbox to finalize and continue on to the next step. However, there's one more fixture that I want to add while we're here. So let's hit Create More Interactions first. Once again, we're going to choose Add a Support/Fixture, Add a Fixture, but this time we're going to select the Roller Slider option. This option allows us to tell SolidWorks that the surface is going to need to stay coplanar with the current plane, or effectively that it can slide around, but it can't bend or change orientation. I'm going to choose this back surface here, because that's where the wall is going to be, and then we can hit the green checkbox. So that's all of the fixtures that we need for here. As with the hinge mate, the hinge fixture is specifically for hinges, so we will leave that one as an exercise to the astute viewer. From here, we've told SolidWorks how the part interacts with the environment, but we haven't said anything about how the environment interacts with the part. So let's add another interaction in. We're going to select the Create More Interactions, and this time choose Add a Load. Once again, we hit the Add a Load button. Here, we can define our load as either a force, something that pushes or pulls our object, or as a torque, something that twists the object. These are books, so we're going to leave it as a force, and then choose the top surface of the object. Next up, we have to define the direction the force is going. We can leave the option set to normal too. This is going to ensure that the force is applied directly on the surface. Otherwise, under Selected Direction, we can choose anything that defines a direction, such as an edge or a sketch entity. Continuing down, we can choose our units. I said pounds, so that's the one that we're going to be selecting here. And then we can define the value of the force. So, these are books. They likely won't be applying their weight evenly across the entire surface of our shelf. But we can make the assumption that the weight will be approximately evenly distributed. So we can leave it as is and just hit the checkbox. We've set our fixtures, we've set our loads. Let's check on the mesh. To do that, we can hit the Done button on our advisor, right-click on the Mesh option over on the left-hand side, and select Create Mesh. At this point, we can set the average density that we're going for, and then hit the checkbox. Oftentimes, the default option is the best one, but there are some occasions where you may want a bit more control. A coarser mesh will run faster, but the results may not be as accurate since you have fewer overall elements. A finer mesh will have more elements, increasing the average accuracy and the computation time. However, this can cause some problems on its own. Smaller elements, especially near corners, have a tendency to report higher and higher values, leading to unstable simulations where the results can blow up to infinity. It's recommended that you start with a fairly coarse mesh, and then double the resolution to see if there are any major changes. If not, your results are probably pretty accurate. Otherwise, keep doubling the resolution until things either start converging to an answer or things start getting silly. Of course, there's a lot more to it than that, but for the purposes of our 15-minute video, this makes for a good rule of thumb. From here, we can hit our green checkbox and see what SolidWorks gives us. These meshes aren't always going to generate the same, so every time you run it, the answers you get may be slightly different, but they're usually fairly close. We can see that everything's been carved up into tiny little triangles. They get a little bit smaller near where the fixtures and the loads are applied, and a little bit bigger elsewhere. This is pretty standard. So, now that we have all three of those things set, We can hit the Run button up on the ribbon to see what our answers are. Okay, well, that's dramatic. Does not look like my shelf is going to make it. However, let's take a bit of a closer look. We can see up here that our deformation scale is set to around 49, meaning that the deformation that we see is about 50 times worse than what we would actually be experiencing. Let's right-click the displacement option under Results, select Edit Definition, and change this from Automatic to True Scale. Now we can hit our green checkbox, and there we go. That looks a good bit better. After all, this is steel. It usually doesn't bend that much in the real world. We can see based on our color plot and on the scale on the right, the furthest deformation that this shelf is going to experience is a little under 2 millimeters. Our books may lean a little bit, but nothing easily noticeable. Let's take a look at our stress next. We can double-click the stress option and take a peek at what our results are. It seems that the largest von Mises stress that we're experiencing is about 100 million newtons per square meter. Well, that's quite the big number, but we can see down at the bottom of the color bar that our yield strength is approximately 220 million newtons per square meter. So we're actually not doing that bad, all things considered. Looks like our highest stresses are occurring around here, at the lip at the front of the bookshelf. So let's get a look at exactly how close our part is to breaking. The values that we're looking for are called the factors of safety, and are the yield stress divided by the experienced stress values of the part. The factor of safety is dependent on the location, so it changes based on which elements of the model we're measuring. However, the total factor of safety of our model is always the yield stress divided by the absolute highest stress the model experiences. It doesn't matter if everything else is fine. If just one bit of this part starts to crack or tear, the whole thing is considered broken and needs to be replaced. So, to look at our factor of safety, let's go up to Results, New Plot, Factor of Safety. From here, we can leave the first two pages alone and set this to show all areas with a factor of safety below 3. The magic number that you want to hit is often industry dependent. Aerospace often looks for values around 2, while civil and mechanical factors of safety can range considerably higher, usually about 5 in buildings and 6 in bridges. A higher factor of safety allows for the forces you expect something to experience to be exceeded without having the part fail, so it is particularly important for things that experience natural disasters or are at risk of being subject to forces beyond recommended limits. However, a high factor of safety often means that more material is being used than needed, and this could add to manufacturing costs and part mass, which is one of the primary reasons that factor of safety in aerospace applications is often fairly close to 2. If the factor of safety ever dips below 1, that means that the material is experiencing more stress than its yield strength. This would result in permanent deformation, increasing the risk of part failure. Anyway, this is an item of furniture, so let's say we have a factor of safety of around 3. That's the value we put into our text box, so from here we can hit our green checkbox, and we can see that the factor of safety dips below 3 pretty much exclusively up here on the front lip of the model. So, what can we do with this information? Areas experiencing low factors of safety should be reinforced. Maybe we can thicken the material, or add an extra supporting strut. Areas experiencing high factors of safety can have material removed, allowing us to lower the weight and the material cost of the part. If we go back to our Model tab, we can see that I've already created a configuration that's made these changes, cutting out large portions of the brackets on the side, and doubling the thickness of the lip at the front. To test the effects of our new changes, we can create a new simulation by right-clicking on the Static 1 option down at the bottom, selecting Copy Simulation, and this time setting it, instead of using the full bookshelf as the configuration, we're going to set it to the stronger bookshelf configuration. From here we can hit our green checkbox, select the Run option, and take another look at our factors of safety, where we can see that nothing dips below 3. To get a more specific idea of what the lowest factor of safety is, we can right-click on that, select Edit Definition, go all the way over to our right tab, and we can see here that the minimum factor of safety of our part is now 3.6. Much better. If those modifications didn't work, we can continue to modify our part, rerun the simulation, compare the results, and iterate until we've gotten a model that we're happy with. From that point, we can manufacture the part and do some real-world testing as needed. Okay, so we've done some finite element analysis, but we definitely used the sledgehammer approach for this one. Oftentimes, it's best to go through the work of optimizing your input before running the simulation. This means looking for planes of symmetry, or modifying your mesh to be finer in areas of high stress. Another way to optimize is by choosing the element properties to best fit your application. Those last two go beyond the scope of this video, but symmetry sounds doable. This bookshelf is symmetrical across the right plane. So if we go back to our model, we can see that we have a half bookshelf configuration where we've gotten rid of one of the halves. And we can once again create a new simulation by right-clicking Static 1, selecting Copy Simulation, and this time setting configuration to half bookshelf. From here we hit the green checkbox, and we have to do a couple of repairs before we can rerun the simulation this time. In this case, some of the fixtures that we've created are no longer there, so we can right-click on the fixtures, select Edit Definition, hit OK, and make sure that there aren't any broken or hanging references in the blue box down here. Everything looks good, so we can hit our green checkbox. From here, we're going to need to add another fixture to take into account the fact that this is going to be symmetrical across this cut. We can do this by right-clicking on the Fixtures option and selecting Advanced Fixtures. The option that we're going to be using is the Symmetry option up at the top, and from here what we need to do is select the surface across which the part is symmetrical. We're going to use this one here. If we zoom out, we can see that we've got a shadow showing us what SolidWorks is going to be simulating, which looks about right, so we can hit our green checkbox. And the final modification that we need to make is to halve the load. We can do this by right-clicking on the force under External Loads and selecting Edit Definition, bumping this down to 100. Once again, hit our green checkbox, and from here we can select the Run button to see that we now get some more accurate results with faster computation time. Once you're done with your simulations, we can go up here and select the Report option, which is going to generate a Word document for us, which is going to generate some plots and all of the information that we've gathered from this simulation. So, there's a lot more to SolidWorks simulations than what we've gone over today, but hopefully this gives you a good starting point to learn even more in future coursework and in your own experimentation. In any case, I think that's where we're going to have to leave things for now. Have a good day, and I hope that you will enjoy the remainder of your academic career.